What's happening, YouTube? We're back again, real quick, with another topic review of my process of working through the curriculum at the Flatiron School Data Science program. If you're new to the channel, if you're new to the series, I am currently a student at the Flatiron School and their Data Science program. It's a coding boot camp, if you're unaware. 5 phases. I'm in phase 3 right now. There's about 10 modules in each phase. I just finished module 25 last night, or yesterday, and I put my notebooks together today. So I kind of put a whole module into one page. As you can see, this one's pretty, well, you can't really see it, but there's not a whole lot going on in this module. It went by pretty quick, so it should be a pretty quick video. Of course, I say that every time, so we'll see. But without any further ado, let's go ahead and jump over to our Jupyter Notebook. Alright, so Module 25, we're going to discuss a little bit of really clarifying like what the difference is between artificial intelligence and machine learning. Because a lot of like non-technical people aren't really aware of that. They kind of use these terms synonymously, and they're not exactly synonymous. We're going to talk a little bit about logistic regression, which is a new type of machine learning model that we learned about in this module. And we'll discuss a little bit about maximum likelihood estimation and the kind of concerns that you need to have regarding that when dealing with particularly binomial data, which is the type of data that we're going to use for logistic regression. So let's talk about AI versus ML and the whole hierarchy there. So artificial intelligence is just, I'm using the word node here, so I'm using that very casually if you're like a real CS mathy person. So artificial intelligence is just like one component, if you will, of the greater hierarchy of computer science topics. Machine learning is a component within the artificial intelligence category. So for example, when you have like NPCs or mobs in like video games, they move around and interact with the environment, interact with the player character using AI software. That has nothing to do with machine learning, right? So furthermore, machine learning can be broken down into supervised and unsupervised learning. And the big takeaway there is that supervised learning basically requires labeled data, which requires some human being to manually at some point sit there and label the data and say it's a bunch of like photos of like, you know, there's like the classic meme of like the dogs and the muffins. I should have gotten that photo in here. Yeah, and so like a human has to go in there and label, this is a dog, this is a muffin, this is not a dog, so on and so forth. So this is a cool little visual just kind of showing the broad hierarchy of machine learning. And we've covered so far in the program a few of these things. Decision trees we haven't gotten into yet. We're going to neural networks, ditto, nearest neighbors. This should say naive Bayes. That's a typo. It says boys. Naive boys. I think we're going to do a little bit with support vector machines and clustering and unsupervised learning. We're going to do a little bit of that. You can see there's some overlap here too. So a lot of these are like neural networks, for example, or what's another one? I just saw one. Support vector machines are classification and regression. There's, you know, very more specific models like within that. So like regression has, you know, so many of these different types of things. And of course there's different types of decision trees within that. So turtles all the way down, so to speak. So for this module, we're specifically talking about supervised machine learning. And there's a few things you need to be aware of when you're dealing with supervised learning. So that's everything under this little node right here in our tree. So classification or regression, if it's supervised, you need this stuff. It requires labeled data, which I mentioned is, you know, some human being actually going in and labeling the data, so the computer has some, or the model or has some control group to like test its predictions against, basically, right? So you need like some set of data that is like correctly like predicted or labeled, in other words, and you need a human to do that. maybe one day we'll eventually. I'd anticipate that we will get to a point one day where we don't need like direct human supervision of labeling data. But anyway, supervised learning also, as our tree displays right here, breaks down into two further broad categories: classification and regression. Regression is what we've done so far in the program. So like our linear regression, and pretty much that's that. We've only done linear regression so far, but we've done lasso and ridge regressions, which are forms of linear regression. So that's where you're kind of predicting continuous. Your target your y is like some sort of continuous variable. So if you're predicting like housing prices, for example, is it $50,000? Is it $150,000? So on and so forth. If a house is $50,000, it's either a steal or it's a very bad house. But anyways, you get the idea that with regression, typically you're predicting something that the target could occur anywhere across like some continuum. All right. Versus classification, it's more like the example they use in this module quite a bit was like heart disease, whether you're predicting if somebody has heart disease or not. There's like two categories. They either have heart disease or they don't. There's no such thing as having like half a heart disease, right? Or 3/4 of a heart disease or whatever. So in this module, we deal a lot with stuff like that. That's binomial, meaning there's like two, or binary, meaning there's only two categories. But there are like other classification models that exist that can predict across like multiple categories. If you're trying to say like I've used in the past like categorical variables to predict as predictors in regression models. So you have like when I did the real estate linear regression model for my phase 2 project, there was a few different predictors that I had that was like the condition of the house, which was maybe on a scale of like 1 to 5 is 1, 2, 3, 4, or 5. So there's no like 1.5 or anything. It's like either 1 or 2 or 3 or 4 or 5. So imagine like if you kind of reverse the roles there and you're trying to predict that category instead. Right. That's basically what you're doing with classification. And of course, any sort of supervised machine learning model, you're going to have some sort of loss function, which we've seen before. So if you're really curious about that, go back to some previous videos. And you're trying to optimize against that. And we'll kind of get back to that a little bit when we talk about maximized likelihood estimation. So let's get into logistic regression. So logistic regression it classifies data, but it actually does it using a regression line. So it's kind of like a hybrid model. And it does that using a sigmoid curve, which you'll see here in a second, which is basically the kind of like logistic, the logarithmic like S curve that you've seen before. Probably if you are like a mathy person. So you've seen like this are like beta hat 0 plus beta hat 1 to the x. You've seen that little chunk or term, if you will, before in our linear regression functions. And I'm not going to get into, I've killed a lot of time in previous videos really going into like the calculus and the proofs and everything, and that's kind of out of my depth, to be honest, as well as not really like the purposes of these videos that I'm making. So you'll notice that we have E here, which is Euler's constant, which is just a constant in mathematics, so like pi or I guess is a constant. But anyway, so so we can work backwards from this, right? This is basically showing that the probability of one outcome or the other for a binomial set is equal to this function here. And so you can imagine like if the probability of an observation belonging to one class, the probability that belongs to the other one is the complement of the probability that belongs to the one class. So we have both of our possible observations on this side, and we would do that by taking the natural log of something. I'm just going to put in the number 10 here, but pretend that this 10 term is like the beta hat plus beta hat, blah, blah, blah. So that, and the natural log of 10, writing the natural log of 10 is literally the same as saying like log base e of 10. Right, so that's all natural log is it's the log base of e of whatever your term is that you're dealing with. So because we have our e constant here, we can solve backwards from this equation using natural log, which is what logistic regression does. So we've seen this before, a linear regression, a whole lot of times. You have some cluster of data that apparently has some linear relationship, and you fit this line to it. And what you do when you fit the line is you're trying to optimize the residual sum of squares in your mean squared error. So if you measure the distance from any one of these data points to the regression line, you take the absolute value of that, you square it, you sum it all up, you get your residual sum of squares, and you want to make that number as tiny as possible, basically, right? So you can imagine if I rotated this line so it's going like this way, so a lot of these data points would be like way further off from the regression line, which would increase our error term. And so that's what you're doing when you're fitting a line, is you're kind of translating this line up, down, left, and right, and rotating it until you get the least error term possible. Excuse me, I'm sleepy. So obviously that can have some issues, or won't fit very well when you're dealing with binomial data, where it's fitting one category or the other. And also take note here that we have a category at 0 and a category at 1. There's no like 0.2, 0.4, 0.6, 0.5. We're predicting with a logistic regression, we're predicting the probability that an observation belongs to one class or the other. So that's why we use a scale of 0 to 1, because in probability theory, that's a pretty like standard thing, is that you measure probabilities on a scale of 0 to 1, as opposed to percentages. So like instead of like 90%, we just say like 0.9. So anyway, this is about as best fit as this line's gonna get for this data, but it's still pretty bad, right? We don't even need to go into the mathematics of it. You can visually see that this line does not fit the data very well. So that's where sigmoid curves and logarithms come into the picture. Where'd it go? There it is. So we use this sigmoid curve to fit the data. So you can see this probably could be fit a little bit better, but you can see there's also some overlap here where we have like some data points here that our curve would predict that they would actually belong to this class, and like vice versa, and that's why you actually get the actual curve here in between like our two peaks, or our limits rather. So this is how we classify binomial data using a regression line. We kind of apply logarithm to that regression line. So that's really cool. And what was really interesting to me is, as I was going through the curriculum, I was starting to think like, I was imagining like, well, there must be some situation or some distribution of data where a straight line isn't ideal, and we could use like some sort of curved line. Lo and behold, like the next module after that thought occurred to me, we're dealing with this right here. So that was pretty cool. For me, just kind of feeling like I predicted it a little bit. Maybe my brain's a machine learning model making predictions. But anyway, yeah, so that's visually what a logistic regression looks like, as opposed to a linear regression. And it should be pretty clear the difference in the kind of type of data that you would use for one or the other. So I'm not going to go a whole lot into the code for this module because there wasn't a lot really. But are you okay? That's my dog back there choking on a bone or something. You good? Yeah, you're good. So, Zeus, are you okay? Okay. So, this is our function for the sigmoid curve, and we can code it pretty simply. So first, we're going to define our function in Python. Do I have a kernel set up? I do. We're going to define our function in Python, and so this whole everything on the right side of the equal sign here is right here. So we have our 1 over, and I enclose it in parentheses just so Python knows like what goes with what. 1 plus, you can call e with numpy using np.e, pretty simple. Our double asterisk to bring it to the power of, negative x. So we have our formula here. We run that. Now we have that function defined. And now we're going to plot it. So we create some vector space for x. And then we plot it using our sigmoid function. And then we get a cool little sigmoid curve like this. So, yeah. Pretty nifty. So let's talk a little bit about maximum likelihood estimation. Maximum likelihood estimation finds the underlying parameters of a distribution to maximize the likelihood of the observations. So that's basically referring to what I mentioned earlier with we're optimizing against our loss function. Those are statements are basically referring to the same thing. So if you're into the calculus, it's right here. That's a lot of calculus. My LaTeX is pretty weak. LaTeX is the coding language you use to like write these formulas and stuff. So this all belongs with this yi right here. We're not actually multiplying this whole term by this. Just by the way, if you get into the notebook, you can probably find a better written formula on the internet somewhere. It's also important to note that the maximum likelihood of a binomial sample is the observed frequency. So if you have a coin and you flip it 100 times and you get 55 tails, and all you have is that one sample of those 100 flips, then your maximum likelihood of tails is going to be 55%. But if you had like multiple samples of 100 flips, then you're going to have like, 45 tails here, 55 tails here, 78 tails there, and then your maximum likelihood is going to be the observed frequency of all those samples. All that to say that a model and its output is simply reflective of the data that is fed into it, right? And that, when you're talking about just like heads and tails on a coin toss, that might not seem like a big issue. However, there can be some pretty serious ethical concerns that come up when you're dealing with machine learning in the real world. For example, considering if you're trying to predict likelihood to exhibit criminal behavior, if I'm trying to be really sensitive about how I talk about this. So say like in the past you had a bunch of bad cops and they arrested a bunch of people wrongfully of a particular ethnic group. Then now that data is in the database that these people of this ethnic group and whatever other background details they have about them were criminals, and that data is fed into the machine learning model. The machine learning model is going to be more likely to predict like people of that background as criminals. It's going to consider among all the other like things, their ethnic group as a predictor for a positive predictor for criminal behavior. Obviously, that's not exactly true. So, going back to like the last video where we talked about data understanding is kind of where you start. You start with your business understanding. You start, and then your data understanding. That's part of understanding your data, is understanding like how was your data collected, and like was it collected, was it input like properly, was there bias in the collection of the data, was there bias like in the input of the data, like human bias, and if there was, which there always is, that's going to contribute to the bias of the model, right? So, and this is particularly problematic when you're dealing with binomial data like this. So, yeah, that's maximum likelihood estimation. Just be really careful about the data that you source and how you deal with the data, and be aware of any kind of biases that might inadvertently occur in your model. So let's just review real quick. AI, ML, machine learning is just a type of AI. There's a whole world of AI out there. Machine learning is just one tiny part of it. We have supervised learning, unsupervised learning. Right now in the program, we're focusing on supervised learning and particularly classification. We've just done a bunch of regression. Currently, we're focusing particularly on a logistic regression, which is a regression, but it's used for classification. So it's a little bit of you get the best of both worlds there, so to speak. A little bit of Python code for you if you're interested in it. Oh, I forgot to mention, with your supervised learning, requires labeled data, and you need not only, I did write it in here at least, you need not only positive examples but also negative examples as well, right? So you need things that like back to the dog and muffin example, you need something that like looks like a dog but isn't a dog, and you need it to be labeled like appropriately. So that's important to remember, that you need positive and negative examples for your labeled data. Logistic regressions used to classify. It's a regression model used to classify data. Be really careful, and just be really mindful of your maximum, the data that you're feeding in, and how that affects your maximum likelihood estimation for any given parameter in your data. Yeah. So, real short video today, a lot shorter than the rest of them. Hopefully I can keep them this short, because I don't think anybody wants to listen to me rant about weird math stuff for 45 minutes at a time. I certainly don't. Let me get my screen cleaned up here. Yeah. I hope you guys enjoyed it. Hope you got something out of it, or learned something, or at least got, piqued your curiosity a little bit. As always, I highly recommend Flatiron School. Calling it a boot camp does not do it justice. We're learning a lot more here than just simply how to code, and that's really cool to me. A year ago, I wouldn't have ever even thought I would ever touch calculus, and here I am making some YouTube videos that there's a little bit of calculus in there, and I'm actually talking about it. So that's kind of cool. Yeah. This is the Flatiron School Data Science Flex program that I'm working through. If you're curious, I'll link the website to their info and everything down below, along with if you want to explore this Jupyter notebook, as well as any of the other Jupyter notebooks or the actual labs and things that I'm doing for the program. That's all available on the GitHub repository, which will be linked below. And if you would like to reach out and contact me for any reason, if you have any questions or whatnot, I'll link my LinkedIn down below, and you can contact me there. So until next time, keep on doing data science. All right, bye YouTube.